You've got a job designing a floating offshore platform. This could be the sort of platform that is increasingly proposed these days for offshore wind turbines. They're running out of space on land in many countries to put wind turbines, so they're now proposing to have them floating. It's also possible that it could be the sort of floating offshore platform that is used to generate electricity from ocean waves themselves. Whatever the case, we're told that this floating platform is in a region where the waves generated by the winds typically have a wavelength of about 6 meters. And we're also told that the water in this region has a depth going down to the seabed here. The depth is 100 meters. There's the seabed. What the question is asking us is, what is the frequency with which these waves will hit the floating platform? Maybe the floating platform naturally wants to bob up and down with a particular resonant frequency that depends on the buoyancy and its weight. It may also have a frequency with which it wants to rock, which is similar to the frequency with which the waves are going to hit it. In any of those cases, you could get a resonance and the whole thing could become unstable. So we want to work out what is the frequency of these 6 meter long waves. So to do that, we're going to use the dispersion relation, which relates wave number to frequency. Now, that is a relation which has the hyperbolic tangent function in it. That's a little bit complicated to evaluate, but we do know we've got the two approximations, the shallow water approximation to the dispersion relation and the deep water approximation. It's a pretty good guess that in water this deep, we're going to be able to use the deep water approximation. But let's first check, just to make sure. The relation holds true for deep water if the depth of water H is greater than about 0.5 times the wavelength. Now the depth 100 meters, that is certainly a lot greater than half the wavelength, 6 meters. So we're definitely safe to use this formula in this case, but it's worth checking. Now that relationship, the approximate relationship for deep water, is the square of the frequency in radians per second is equal to the acceleration due to gravity, g, times the wave number k. Now the wave number k we can figure out straight away because we're told what the wavelength is. The wave number is 2 pi divided by lambda, the wavelength, and that turns out to be about 1.02 reciprocal meters. So now that we've got the wave number, we can plug it straight into our approximate, remember it's the approximate dispersion relation for water surface waves. I'm going to take the square root. I'm going to use the acceleration due to gravity of about 9.78 meters per second, multiplied by the 1.02 we just calculated, and the result is a radians per second frequency of about 3.17 reciprocal seconds. No point quoting this number to very many digits because we've only used 3 significant figures here and here. So now we can easily work out the frequency in hertz, which is our most used to engineers. The frequency would be the radian frequency divided by 2 pi. And that turns out to be about 0.5 hertz. 0.5 hertz is the answer. So if our platform tends to rock or tends to bob up and down with something like 0.5 hertz, we could be in trouble. So the aim would therefore be to design this such that its frequencies of bobbing up and down or rocking are nowhere near the frequency generated by the impinging waves.